Good afternoon, everyone. Welcome to the CICES webinar. I will just pause for a moment or two until we allow some more attendees in, and I can just see the attendee list is increasing as the moments pass. So we'll give everybody maybe till 2 or 3 minutes past to join, and then we will kick off the presentation. Okay. Okay, everyone. I still see the people who are joining this session, but I will kick off with a few of the introductions, etc. So welcome everyone for those that have taken the time to attend the webinar today. On behalf of the CICES Ireland and Northern Ireland region, I am Richard Bell. I'm the regional chair for the region for the current period, and we have organised this webinar today for the Gull project, the construction of the world's largest rolling bascule bridge, constructed by Farrans Construction. Just before we start, an early special thanks to Tristram Browne, who is one of the presenters today, the project manager on the contract itself, and Ross McWha, who is our head of engineering, both at Farrans Construction. If there's anyone on the call, just a quick call out for the Northern Ireland and Ireland region. Any members on the call today, we have our next regional committee meeting next Wednesday. If anybody would like to join and attend, please reach out, and we encourage attendance at some of our future events of the Golf Day in June. We have an upcoming visit still to be planned and hit the website for the visit to Narrowwater Bridge, currently being constructed by BAM in Northern Ireland. So we have an exciting rolling calendar of events for the rest of this year. At the end of the presentation, once we are finished, we will have a short Q&A session. So please put some of your questions into the chat if you have any, and if we have time, we will address some of the more pertinent questions. And finally, the presentation, which will be given today, can be shared for any interested attendees. So again, please reach out to CICES headquarters, and we can share it to anybody who has attended today if of interest. So without further ado, we've given another moment or two to allow people to join. I'd like to hand over to Tristram Browne and Ross McWha, and Tristram will be our first presenter on this webinar. Thank you, Tristram.
Thanks, Richard, and thank you to the institution for the invitation and the opportunity to present on the Gull project, and thanks to you all for taking the time to join us this afternoon. Today our presentation is about the Gull, constructing the world's largest rolling bascule bridge. As Richard has pointed out, presenting to you today, representing Farrans Construction, are myself, Tristram Browne, the project manager for the construction of the scheme, and Ross McWha, the Farrans engineering manager, and managed the design on the project. Although we're here to give an insight into the Gull project, it is of note that Farrans constructed 3 of the 4 moving bridges delivered in the UK last year. The Gull Bridge at the top, the Govan to Partick Bridge in Glasgow, seen in the centre photograph, and the Herring Bridge in Great Yarmouth, seen in the bottom photo. The agenda for this presentation will cover the following: an introduction to the scheme, including high-level information about the purpose, benefits and the major elements of the scheme. We will discuss some key construction activities, highlighting significant elements and the wide range of construction techniques employed in their delivery. Challenges. This was a technically demanding project which presented many challenges to our team. Today we'll focus on the NAV1 install, the marine cofferdam construction, including Pier 4 specifically, and the bascule bridge span installation. And to wrap up there will be a question and answer session. So if you have any questions you'd like us to answer, please can you type them into the chat box and we'll try and answer as many as we can at the end. So let's get straight into the main subject of this presentation, the construction and associated challenges faced in the delivery of this landmark project. The Gull Bridge opened to the public on the 7th of September 2024 and is the third crossing of Lake Lothing. Its main objectives are to encourage opportunities for regeneration and development, to provide additional capacity to support growth, reduce congestion in the town, to reduce journey times and improve reliability of those journey times. This will improve the connection between the communities north and south of Lake Lothing. This is a project that the locals have been campaigning for over a generation, and it has finally been delivered and welcomed by the local residents. The Gull Bridge is located in Lowestoft, a coastal town in Suffolk and the most easterly point of the UK. The new bridge provides an additional crossing of Lake Lothing, which forms the inner harbour of the port of Lowestoft, connecting the Waveney River and the Broads National Park to the North Sea, effectively cutting the town in half. Until now, there's only been two crossing points: the A47 bascule bridge on the east, located at the Sea Harbour, and the Mutford Lift Bridge on the west at the mouth of Oulton Broad. To the west of the town are the rail connections in red, which also affect traffic flows as there are two level crossings on the main traffic routes. So as you can imagine, with marine traffic from the operational port and recreational vessels entering and exiting the Broads National Park, the regular rail services interfering with traffic routes, the journey time for local traffic are frequently impacted. This new crossing provides more reliable journey times as it bridges the rail line and provides 12 metres of clearance at high tide, which is nearly 4 times that provided by the A47 bascule, thus significantly decreasing the number of bridge openings required per day, maximising the availability of the route to road traffic. The project is for the construction of an 8-span viaduct, including the rolling bascule, with roundabouts to the north and south. It provides a single carriageway road with cycle and pedestrian facilities on both sides of the carriageway. Looking at the slide and working from right to left, to the far right, we have the southern roundabout connecting the new bridge to Tom Crisp Way and Waveney Drive, and the new roads constructed for access to existing businesses, as the new bridge is built on the footprint of their existing access road. This leads to the south approach embankment, a reinforced earth embankment connected to the south abutment. Then we have the south approach viaduct, or SAV as we call it. The SAV has 4 spans supported on the south abutment and 4 piers, the last of which, Pier 4, is located within Lake Lothing. The final span onto Pier 4 is responsible for taking the majority of the load of the bascule bridge, which rolls back onto this span when opening. The control tower is located adjacent to the south approach viaduct. This is a 7-storey building with adjacent plant rooms situated beneath the bridge deck. Between them, we house the bridge operator, the hydraulic pumps and all the equipment required to operate the bridge, as well as a backup generator. The bascule span, supported between Piers 4 and 5, located within Lake Lothing, is a 39.5 metre span. It is a single leaf rolling bascule and the largest of its type, powered by hydraulic cylinders. Then on to the north approach viaduct, which has 3 spans supported on 3 piers in the north abutment. This crosses the East Suffolk railway line and commercial port facilities to reach the north abutment. The north approach embankment is supported by concrete retaining walls, which are clad to match the reinforced earth walls of the south approach embankment. Then on to the new roundabouts and roads to connect the bridge to Peto Way and Denmark Road in the north. The ground conditions in this area are particularly poor, and to deal with this, the embankment and roundabout sit on some 1,200 deep soil mixed columns topped with a load transfer platform. To give an idea of the scale of the project, here are some of the high-level figures. There's more than 2,250 tonne of structural steelwork was fabricated and installed between the approach viaduct and bascule spans, of which the bascule span contains circa 650 tonnes, and that doesn't include the 400 tonnes of counterweight concrete. The bascule raises in 116 seconds and lowers in 106 seconds.
Thanks, Tristram. I'm going to give you an overview of some of the key construction activities whenever we want to construct the bridge. The first is piling and ground improvement. Piling was amongst one of the first operations to commence, with several different types of piles and methods required. On the left photo, you can see the arbor push piles for the eastern protection dolphins to the piers. These were steel piles which were screwed into the lake bed using an arbor push technique due to the proximity of a UK Power Networks tunnel, which required us to minimise vibration. To install the piles, we required a static platform in the form of a jack of power, which you can also see in the image, the piling rig sitting on it. Hydraulic drop and vibration hammers were used to install the other steel tubes and sheet piles for the marine pier cofferdams on the western dolphins, with a total of 184 piles in total. The image in the centre shows the installation of the cofferdam for Pier 4. Rotary board piles were also required for the marine pier foundations. These piles were installed through the steel combi tubes, and are up to 65 metres in length. Landside, we required approximately 170 number continuous slide over piles for the land-based piers and structures. These were 1,200mm diameter and ranged between 25 and 30 metres in depth. The image to the left shows installation of piers by the piles to the control tower and the plant room. The central image shows the piles installed for Pier 6 being cropped down to size, and you can get a real sense of the scale here with the mini-digger in the foreground. And then the right-hand photo shows the deep soil mixing. There were some 1,200 deep soil mix columns which were installed below the northern approach embankment as a ground improvement technique, and these were then topped with a mass mixed load transfer platform. A deep soil mix column adjacent to the north abutment can be seen in this photo being installed. There were numerous and significant concrete structures required across the project, some which can be seen in the photos on screen. The image on the left shows Pier 3, the plant room immediately behind it, and the control tower to the right-hand side. Pier 2, Pier 1 on the south abutment, and the south approach in the background behind. The image in the centre shows Pier 4 completed with the south approach steelwork in position and the placement of the permanent formwork ongoing. And the image on the right shows Pier 5 in the foreground supporting the span nav 3. You can then see nav 2, and finally you can see span nav 1, which crosses the railway with its deck and its parapets already completed. Tristram will come to in a moment. And beyond that, you can see the northern approach embankment. Temporary works were critical and a very significant element of the construction works that we carried out. All of the viaduct sections in the bascule span were manufactured off-site in Belgium by our supply chain partner, Victor Bouygues Steel Construction. The viaduct sections were delivered in 3 stages. Span nav 1 delivered first, which was installed over the railway during a planned possession. Spans nav 2 and 3 were next to be installed, closely followed by the 4 southern approach viaduct spans. These were all transported to site by barge, installed by crane. Various sizes of cranes were used, the largest being the CC 8800, which has a 1,750 tonne capacity, and was used to install the southern approach spans. This crane is one of the top 10 largest crawlers in the world. The bascule was then delivered last, and this was installed directly from a barge without the use of craneage, and further detail will be provided later on. The image here on the left shows span SAB 3 being installed with the CC 8800. The image in the centre shows one of the two cylinders being installed into the cylinder pit, safe at Pier 4. The cylinders are substantial items, weighing approximately 60 tons each, and they have to be lifted, orientated correctly, and secured within the cylinder pit prior to arrival of the bascule. And the image on the right shows the bascule span itself being moved into position by barge. It's worth noting that we had a 3-week channel closure to get the bascule into place and operational, as the channel had to be reopened to port traffic by the end of that 3-week period.
Thanks, Ross. As Ross talks through these quickly, it sounds straightforward. It wasn't. Each of these elements presented their own challenges. There were physical constraints, both on and off site, that had to be dealt with. Each demanded detailed coordination with numerous suppliers and stakeholders located across the UK, Europe and beyond. Constant review was required across the site of progress, phasing and interfaces to ensure the coordination of the site activities, logistics for moving the sizable elements of the bridge across from Europe, and the preparation of the temporary works required for the heavy lift plant required for installation. Next, I'll talk through a number of these challenges, how they were managed and overcome. The Gull Bridge project had many interesting and varied challenges throughout. Today, I'm going to focus on two of the most challenging parts of the project. The first is the North Approach Viaduct Span 1, or NAV1 as it was more commonly referred to. NAV1 is a curved viaduct span constructed on CFA piled reinforced concrete foundations, the north abutment and Pier 7. The deck is designed as a composite structure made up of a structural steel ladder consisting of 2 longitudinal main girders with transverse cross girders combined with a reinforced concrete deck. Some key statistics around this span are: the span is founded in 30 1.2 metre diameter continuous flight auger piles, 25 to 30 metres deep. 2,100 cube of concrete was poured in the foundations between the piles, pier and abutment. There's a 55 metre span between the north abutment and Pier 7. There were 290 tonnes of structural steel used in the span, and 460 cube of reinforced concrete was used between the deck and the parapets. The key constraints in this area were the East Suffolk District Railway, which included up and down lines plus working sidings. As part of the client's agreement with Network Rail, a single 52-hour weekend possession of the railway had been agreed to allow for the installation of this bridge span. Early programme committal was required as possessions of this nature are booked over a year in advance. All on-track and adjacent line working needed to be approved by Network Rail and in accordance with their engineering management for project and engineering and architectural approval for building and civil engineering work standards. All design submissions had to be submitted using the Network Rail Forms 1 to 3, and all works had to have an accompanying Network Rail Work Package Plan style method statement. As part of the Network Rail approvals, a 24-hour track monitoring system was required to monitor the track for any potential settlement. We set up an automatic total station and 300 track-mounted measurement prisms for this purpose. Commercial Road is the single and only road servicing the Port of Lowestoft. It is owned and operated by Associated British Ports. Commercial roads had to remain open 24 hours a day so as not to impact on ABP's port operations. The key constraints in this area were, NAV1 has been designed so that the deck could be poured offline to minimise the amount of interface with live railway. Farrans elected to use our specialist structural steel contractor, Victor Boyk Steel Construction, to fabricate all the major bridge spans off-site in Belgium. The completed spans could then be transported to Lowestoft by barge. The structural steel would arrive by barge and then be offloaded using self-propelled modular transporters, SPMTs, and moved to a temporary storage area between the railway and Commercial Road. Once supported on 12 temporary trestles, the concrete deck and the high containment concrete parapets could be constructed. The bridge would then be jacked up 6.5 metres in the air above Pier 7 and north abutment bearing shelves and transported into position using a larger combination of SPMTs than was required for the bare steel offload, as the bridge would now weigh over 1,400 tonnes. On the Gull Wing project, which was of significant size and complexity, there were many hundreds of temporary works designs required. For NAV1, some of the key designs required included piling and crane working platforms, a well point dewatering system to facilitate the pile cap excavations due to the high groundwater table, and an associated geotechnical dewatering analysis to assess impact on the railway track support zone. Excavation support was required for the north abutment and Pier 7 pile cap construction. The support design at Pier 7 required a sheet piled wall adjacent to the railway boundary, which you can make out in the central photograph. A temporary raft foundation support slab for the offline deck construction area was required to ensure no differential settlement occurred during the incremental application of construction loads, as this would be locked into the deck once cast. Working platforms and track protection designs were required for operating the SPMTs. For the main installation, 2 rows of SPMTs with 16 axles on each row were required at each end of the NAV1 span to manoeuvre the 1,400-tonne bridge into its final position. You can also see to the left of the photo the temporary diversion of commercial roads, which was required to create the space required to pick up and rotate the bridge, ready in advance of the railway possession in the final installation phase. This slide shows the installation of the temporary track protection system, which involved removal of some of the key items of the railway signalling system, timber protection around the railway points and trackside cable troughs, covering the railway tracks with ballast to create a smooth and level working platform, creating a load spreading platform with timber spreader mats, creating a smooth running surface for the SPMTs with an aluminium trackway system. The design approval for this protection system took many months of optioneering, discussion and risk analysis with Network Rail, as it's not a commonly used method of track protection. It was chosen as it provided the greatest load spreading properties and involved a relatively quick and simple installation and removal methodology to allow us to complete the works within the allotted possession time compared to some of the other options considered. This slide shows the completed track protection system, ready to commence the final installation phase with the SPMTs. This slide shows NAV1 on the move. This slide shows NAV1 in place between the north abutment and Pier 7, still on the SPMTs while the load was being transferred to the bearings and the temporary restraints which held the bridge in a safe position while the bearings were grouted and cured to fix the bridge in position. The inset at the bottom right of the photograph is a picture taken at the end of the possession with the track protection removed, ready to reopen the railway line to trains. The next construction challenge that I want to talk about today is the construction of the marine cofferdams for Piers 4 and 5. The design for the Pier 4 and 5 cofferdams was for a steel piled combi wall arrangement, with Pier 4 wider to accommodate the additional space required to contain the hydraulic cylinder pit. The cofferdams were designed to be constructed using a combination of 1200 mm diameter steel tubes and AZ27-800 sheets, all 16.5 metres long with a tow level of -14 metres AOD. The design made provisions for the steel cofferdam with the inclusion of a reinforced concrete plug in the base, which had to be constructed in the wet, to function as a cofferdam to facilitate dewatering to a level of -5.5 metres AOD in Pier 4 and -2.5 metres AOD in Pier 5, allowing construction of the pile caps and pier foundations below the waterline, and then to remain as the permanent footprint to contain and protect the pier foundations. Some of the key constraints and considerations associated with the marine piling operation were: Piers 4 and 5 are located in the marine environment of Lake Lothing, approximately 30 metres from the south and north quays respectively. a UKPN network power networks service tunnel, 2 metres in diameter, carrying critical power and communications cabling, was located 5 metres from the line of the eastern dolphin piles and 7.5 metres below the dredged channel bed of Lake Lothing. A 32-metre wide clear navigation channel had to be maintained 24/7 to allow the Port of Lowestoft operations to continue. This was a condition in the development consent order issued by the UK government for the project. The South Quay was unstable. This is an unmaintained quay wall with corroded piles and large voids behind them, caused by the washout of backfill material. Farrans constructed the marine cofferdams using conventional marine piling techniques. The steel piles were installed by utilising a temporary piling frame, Farrans in-house heavy lift crane barge, and crane-suspended vibro and hydraulic drop piling hammers. A piling sequence had to be planned to ensure that at each stage the placement of marine plant allowed for the 32-metre clear navigation channel to be maintained to allow the unrestricted commercial port operations to continue. No spud legs from any of the barges could be located within 10 metres of the UKPN tunnel on the bed of Lake Lothing. Vibration and settlement monitoring of the tunnel was required throughout the marine construction phase of the project to ensure the works that were not adversely affecting the tunnel. Sufficient space had to be maintained from the South Quay wall, of which there was a high risk of collapse. This prevented dredging along the front of the quay, which would have made marine plant positioning easier, but as it was, there was a shallow lake bed close to the South Quay, restricting the available plant that could work in that zone. In this photograph, you can see on the left the Farrans crane barge working on the steel piling for Pier 5 with a piling gate installed for tube installation. Pier 4 on the right has already been completed with all steel piles installed, along with the temporary access walkways which we installed, utilising the permanent dolphins protection piles as supports, ready for the next stage of construction, the rotary board piling. The ground investigation borehole showed the ground conditions were made up of a layer of alluvium overlaying a 10 to 15 metre thick layer of Happisburg clay, with the crab groups, granular, sandy material found below this to depths of about 65 metres, where the deepest borehole ended. The ground conditions were particularly challenging, with blowing sand picked up during the ground investigation phase. The piers were designed to be supported in 42 rotary board piles, 1.08 metres in diameter, ranging between 24.5 and 62.5 metres of working length, which meant piles of up to 65 metres below platform level. The longer piles providing a greater degree of skin friction to support the extremely high loads exerted from the static and cyclical movement of the bascule bridge span above. As the permanent cofferdam had not been designed to take any additional loading, an independent temporary piling support platform was designed and installed along with the permanent cofferdam piles. You can see in the first photo the 610mm diameter bearing piles within the cofferdam used to support the piling platform, which had to be 32 metres long to achieve the bearing capacity required for the design. The second photo shows the steel platform being installed, and the last photo shows the piling rig being moved onto the platform from our heavy lift barge. Due to the length of the rotary board piles combined with the ground conditions, a polymer support fluid was required to maintain the bore while the piles were constructed. Quinn Piling were contracted to carry out the rotary board piling under polymer due to their experience and expertise with working in similar environments before. These piles, however, were exceptional due to the site-specific conditions and the required pile lengths. You can see in the photographs here the piling rig working on the Pier 4 cofferdam, boring piles down through the steel tubes of the cofferdam. On the quay, the blue polymer tanks and testing lab. Maintaining the correct polymer consistency and head levels was critical to maintaining the bore and preventing build-up of our filter cake around the bore's perimeter, which could impact on the skin friction and ultimate capacity of the piles. This required a 24-hour polymer testing and maintenance operation. You can also see the compensation tank on the platform, which was connected to the pile, and used to maintain the required head of polymer to keep the bore stable. The pilar risings were discharged into boat skips and lifted to shore using the white 250-ton crawler crane with luffing jib, while rebar cages, concrete tremies, etc. were handled by the 130-ton and 40-ton crane barges. You can also see Pier 5, which has the platform frame installed and is waiting on the deck matting, and the Pier 6 pile cap excavation, which also required a cofferdam due to the proximity of the quay and the adjacent shed, as well as the plant room under construction behind Pier 3. I shall now hand you over to Ross, who will take you through the construction of Pier 4 and the bascule bridge.
Thanks, Tristram. Well, you've just heard about construction of the cofferdams and the associated piling works, and I'm now going to pick up on the construction of Pier 4, which the cofferdam facilitated, and installation of the bascule span, which is located on top of Pier 4. Once the rotary board piles have been installed and the temporary works platform supporting the piling rig demobilised, excess material from inside the cofferdam was removed and a concrete plug poured in the wet. This allowed the cofferdam to be pumped dry whilst avoiding the risk of flotation. Construction could then begin on the reinforced concrete pier, which supports the bascule and houses the hydraulic cylinders which open the bridge. This photo shows the works to cut down and remove the inner perimeter of the steel combi wall tubes, which subsequently allowed the rotary board piles to be broken down and the exposed reinforcement tied in the base slab of the pier. A temporary whaling system can be seen, which held the opposing cofferdam walls apart. This wasn't required for stability, as would be normal for a cofferdam, but it was necessary to maintain the line of the cofferdam to ensure that the preceding concrete works were on the correct line and plan. The flexion of the severed tubes had been calculated at 100 millimeters, which would have resulted in the span being too short, not being prevented. The photo here on the left shows the pier stem, just as the concrete works protrudes past the top of the cofferdam. Mass infill concrete is also shown, which fills the void between the steel piles and the pier stem. Mass infill is split into two lifts, which meant that the whaling beam on the previous photograph was able to be removed prior to the second pour. The image on the right is that of the completed pier, with span sab 4 cast into the pier stems. You can also see the cylinder pit, as well as the notch out of the bascule tongue on the deck. The inset photo here shows the cylinder pit when viewed from above, and the base plate for the bottom cylinder clevis plate can just be seen. As we previously noted, all of the steelwork was fabricated in two Victor Works factories in Ghent, Belgium. The bascule steelwork would have been too tall to allow the J-beams to be welded in place in Belgium due to the restricted height clearance below the bridges in the Ghent-Terneuzen Canal between Belgium and the Netherlands for the route onward to the North Sea and eventually Lowestoft. The solution was to transport the bascule, deck, and the J-beams unconnected by barge to a Mammut facility in Westorp in the Netherlands, which is downstream of the bridge restrictions. The bascule and the J-beams were offloaded, and the bascule deck was then supported to allow unhindered access to undertake connections of the J-beams. This image provides an idea of the scale of the Gull Bridge against another famous bascule bridge, which is Tower Bridge in London. In the open position, nose end tips of the J-beams are 61 metres above water level. This image shows the bascule in Westorp in the Netherlands. In the background, you can see the blue temporary works frame, which was used to support the two J-beams in the position during fabrication works. The eastern J-beam has already been located and the connection prepared ready for welding. Whilst the bascule was in Westorp, we undertook some additional works prior to delivery to Lowestoft. This included completion of the carriageway deck, the surfacing to the carriageway deck and footways, as well as installation of the parapets. But the main element of works undertaken were to machine J-beam flanges to allow the curved tracks then to be installed. The J-beam lower flanges had been oversized by Victor Boyd by 40 millimeters. That's to say that they were 140 millimeters thick as opposed to 100. This was to facilitate machining of the two flanges to create a perfect 10-meter rolling radius to which the curved track would be bolted. Photo here shows the pivot point on the temporary track which has been welded to the J-beam web, and the cutter swing arm which supports the milling machine can then be seen in the inset photograph, along with the machined J-beam flange which you can see at the top of the inset photograph. With the two flanges machined, holes were then drilled and tapped for the curved racks. They can be bolted into position once the paintwork remedials have been completed. The image on screen here is from a 3D survey completed by Oil Gear and their specialist supply chain to agree the center rotation to ensure that once machined, the minimum flange thickness of 100 millimeters remained, and the two flanges are machined in the same plane at a 10-meter rolling radius. The bascule was then transported to Lowestoft, and as you can see in the main photo, it shows the bascule barge on a barge passing through the existing bascule bridge in the A47 at the mouth of Lowestoft Harbour. We then had a week of activity to prepare for installation between Piers 4 and 5. This included removing the sea fastenings, swapping out some temporary support sections which have been installed in Westhorpe in lieu of the curved track, which allowed the bridge to be supported on the barge without damage. We also then had to rotate the bascule through 90 degrees in the barge, which can be seen in the inset photograph, and this was achieved using SPMTs. You also see in the photograph the cartilage that was used whenever the bridge rotated, as the J-beams are now oversealing the end of the barge. This image shows the barge with the bascule rotated and supported on a mega jack system, which has been raised up so that the bascule deck clears both Piers 4 and 5, the two spans, SAB 4 on the left and NAV 3 on the right. The barge was manoeuvred into position on a Saturday morning in early March 2024. It was then jacked down into position. The cylinders were extended upwards, and thanks to some clever temporary works attached to the clevis plates holding the correct angle, the clevis plates were offered up the lift box on the underside of the bascule, and the bolts were able to be secured into the lift box first time. This photo shows a view from the underside. You can see the two cylinders, you can see the clevis plate, temporary works, and then you can see the lift box and a number of the bolts being put into place. It should be obvious that such smooth installation with no clashes was not left to chance. For over a year previous, we had held weekly tolerance meetings between ourselves, Victor Boyk, Oil Gear and Demir, and the permanent works designer. We tracked all interfaces between the elements. We discussed the impact of each element had on the next, and which party was responsible for that interface. That party was then tasked with bringing more information in terms of surveys and further designs to allow the interfaces to be checked to ensure that they were free of clashes. One good example of this was between the clevis plate shown here, on the top of the cylinder, and the lift box to which it is bolted on the underside of the bascule. Following a fabrication survey, we had to adjust the centre line of the bridge to account for fabrication tolerance. Clevis or lift box is directly on the bridge centre line, but this was adjusted by moving the whole deck by 9 millimeters to the east, so that the J-beams were centred with the two cylinders to keep the loading in balance. This required us to amend the setting out for the tapped holes to the lift box, and these holes were then drilled and tapped onto the underside of the bridge while it was in Westhorpe. The other impact was that the deck concrete works and SAB 4 with the notch had to be moved to maintain a 20 millimeter gap between the bascule steelwork and the permanent concrete. The cylinder shown here in the closed position at a length of just over 16 meters, and when open they extended just over 29 meters. Heavyweight concrete had been specified in the two J-beams with a target density of approximately 40 kilonewtons per cubic meter. That's about 66% heavier than standard concrete. We undertook trials to confirm that target density was achievable, and these were completed alongside our Magnadense supplier LCAB and the concrete supplier Capital Concrete. But we were concerned that the concrete would segregate and may not achieve suitable compaction, hence density was poured into the counterweight compartments, because the only way into the compartment from the top of the J-beam, some 30 meters above the deck. And there's no safe or reliable way to install a tremie tube into the J-beams due to the stiffeners that you can see in the left-hand photo. So we overcame this challenge by undertaking a trial pouring site with a J-beam mock-up, which can be seen in the photo on the right-hand side. This allayed our fears that the concrete would not flow and that it wouldn't segregate. We also took tubes from the concrete at the bottom and we were able to confirm that the density was still achievable during this install method. One area that we had to take great care over was the weight of the bascule. Once the bridge was installed between piers 4 and 5 in the Wistoft, we were going to be tasked with pouring the counterweight in each J-beam. This was just one of the many activities to be completed during our theory closure. The design intent was to add just enough counterweight such that the nose end reaction in pier 5 was reduced to 140 kilonewtons per side with a tolerance of plus or minus 3 kilonewtons. So in the grand scheme of things, the overall bridge weighs 760 tons or thereabouts. You have a tolerance of 600 kilos, plus or minus. And this was all to be done while maintaining a center of gravity, the bridge plus minus 50 millimeters from design COG position. So to do this, we created a load schedule and recorded all the assumed and then the actual weights of the bridge and all its components as it became known to us. And we completed a series of rudimentary calculations to confirm the COG position and the nose end reaction at each stage as the permanent works were installed. This was very useful and it allowed us to identify that the weight of the cylinder and its clevis plate, which had been bolted to the underside of the bridge prior to installing the counterweight, had not been considered in the figures for the overall weight. We needed to allow for these. On the morning of the pour, we installed 2 large load cells at the nose end of pier 5 and commenced pouring the heavy concrete, alternating between J-beams to minimise the out of balance effect. In the photo here, you can see the concrete pump. You can see an access mute highlighted in red is the eastern counterweight compartment, and there's a similar in the west. And the inset photo shows the access hatch some 30 metres up the deck with the concrete pump going in. You can see the 2 operatives on the top of the mute directing the concrete. Whenever we started pouring concrete, the load cells readings we received back during the course of the pour started out very accurate, but became less so as the load in the nose reduced from an excess of 1200 kilonewtons towards a target load of 140 kilonewtons. That's to say that the load cell, for the load cell to be accurate, the load applied needs to be within a small percentage of its overall capacity. So at 5 o'clock on the day of the pour, we went to pier 5 and swapped out the 2 load cells for smaller ones, and after some minor adjustments, we were able to confirm readings of 135 kilonewtons and 133.7 kilonewtons on the respective J-beam nose end. The readings here are shown in tons and they tallied with our design figures. So in summary, there were a great number of other technical challenges the team had overcome, all of which made the Gull a very interesting project to deliver. As an example, we haven't even delved into the mica design, which is a whole set of challenges of its own. The photo you can see here on screen is from the opening weekend in September 2024, when the ride out for the final stage of the Tour of Britain cycle race crossed the bridge. So finally, we'd just like to thank the institution for giving us the opportunity to present the Gull project, and you, the audience, for taking the time this afternoon to listen to our presentation. We hope it's been of interest to you, and we will now take some questions.
Okay, Ross, well, listen, thank you. We'll give people an opportunity to put a few questions in the chat if they want to. I'll just take the opportunity to say thank you again, Tristram and Ross, for sharing your extensive knowledge and experience on what evidently from the presentation has been a very technically challenging project. It was a great presentation in summary, and I'm sure that both yourselves and the wider delivery team may never be afforded an opportunity to work on a project like this in the future, which has such a wide and vast and diverse range of various construction techniques. It's certainly a credit to yourselves and the wider Farrans team to deliver this and adding it to the portfolio of work in the bridge sector that you do. And it's obviously very evident the benefits that it brings to the local community on what is a very and has been a very significant infrastructure improvement for Lowestoft. So thank you. I don't see any questions in the chat, so you have obviously covered it very extensively, Ross and Tristram. I'm just conscious of everyone's time. We did say we were going to cut this off at around the 1:45 mark, so if no one has any questions, we will bring it to a close there. Thank you, everybody. Thank you to those attending the webinar today on behalf of the institution as well. Thank you, everyone.
Thank you.
Thanks, everyone.